Got it. All right. Welcome everyone to this second part of this module of the modeling course of the Thomas Young Center. So this module is focused on how to describe electronic excitations in materials, basically using Green's function theory, and how to calculate these Green's function with Feynman diagrams. My name is Johannes Lischner. I'm a reader in theory and simulation of materials at Imperial College London, and this is my email address. If you have any questions, just shoot me an email. So where it says this week, this is actually last week, where we spent some time giving a sort of more hand-wavy introduction into GW. And after we had sort of motivated theory, we started sort of getting into it more rigorously by introducing the concept of a Green's function. And in just a minute, I will sort of go over what we covered last week in more detail. And then this week, we'll continue with our study of Feynman diagrams, which, as I said, is sort of the means of including electron-electron interactions. And then at the end, I will say a little bit about how GW calculations are carried out in practice. If you have any questions, don't hesitate to interrupt. You can just unmute yourselves and, shout out your questions. Alternatively, I will try to keep an eye on the chat, but I might forget to check that. Okay, so let's see what happened last week. So we first started with asking ourselves, why is there a need to go beyond density functional theory in modeling properties of materials? And the example that we used was photoemission spectroscopy, where essentially you shoot photons at a material, and by the photoelectric effect, this knocks out an electron, and what remains behind in the material is a hole. And what you measure in this experiment is a so-called quasi-particle energy, which is defined as the difference of the total energies of the ground state of the material with n electrons and the total energy of either the ground or an excited state, labeled by this lambda subscript here, of the system when one electron has left the material, right? So that's what's measured in a photoemission experiment. And there are other experimental techniques that measure similar things, like inverse photoemission spectroscopy, scanning tunneling spectroscopy, or transport. And then we thought about how to model a photoemission experiments, and we thought maybe DFT is a good starting point. But then we basically reminded ourselves that the Kohn-Sham energies of density functional theory aren't really physical objects. And this is reflected in the fact that density functional theory often severely underestimates the band gaps of solids. And that led us then to ask ourselves what type of theory we would need to develop, such that we can calculate excited state properties of solids such as band gaps reliably. And the first sort of hint as to what such a theory might look like was the success of Hartree-Fock for predicting quasi-particle energies of molecules quite accurately. So that was, but of course in Hartree-Fock, you have to deal with a non-local Fock potential or exact exchange potential rather than the local exchange correlation potential of density functional theory. So its calculations are more expensive. But despite this, Hartree-Fock is still not particularly accurate for the band gaps of solids. In fact, it quite dramatically overestimates band gaps of solids, while, as I said, DFT tends to underestimate them. And the reason for this is that Hartree-Fock doesn't capture what we know as screening. And that means that when I have a material that contains many electrons, the effective interaction between two electrons contains two parts, sort of the direct Coulomb repulsion, but then there is another part that is basically arising from the fact that the presence of the first electron induces a rearrangement of all the other electrons in the material, which gives rise to a polarization charge density, and that polarization charge density then interacts with the second material, with the second electron at R prime. And sort of in a material where there's lots of electrons, this rearrangement really is an important contribution, while in molecules where there are typically not so many electrons, it is not such a severe problem if we neglect this effect, which is the reason why Hartree-Fock works, reasonably well for quasi-particle energies of molecules. So we need a theory that captures screening and a theory that is also non-local. And this theory is what we call the GW approach, where we replace the exchange correlation potential of DFT with a quantity that's known as a self-energy, which is a non-local and energy-dependent potential. And the energy dependence basically reflects the fact that screening is different for fast electrons and slow electrons. And what is the self-energy? It can be written as a sum of two contributions. The one is a so-called screen exchange potential, where basically what we have done, we have replaced the bare Coulomb interaction in the Fock potential by a screened Coulomb potential. But then there's another contribution, which is known as the Coulomb hole term, which is a local term, a local potential within a certain approximation. And this Coulomb hole term basically captures the potential that acts back on the electron due to the polarization charge that it induces in its environment. So this is the physical interpretation of this Coulomb hole term. Okay, so that was the first part of last week's lectures, where I sort of gave this hand-wavy introduction. And then we started about sort of, trying to derive this GW theory from first principles. And to do that, we had to introduce the concept of a Green's function, which basically required first an understanding of what a field operator is. And a field operator is basically an operator that adds or removes electrons from a material. So we discussed that concept for a little bit. And then the Green's function basically describes the propagation of electrons and holes through a material. So you see here, we, for example, start with the ground state, then we remove an electron at a position r and time t, and add it back in at a later time t prime and at a different position r prime. So what this quantity measures is how the hole propagates through the material. And similarly, we can look at how an electron propagates. And the Green's function basically describes both of these processes, electron propagation and hole propagation. And so this is the reason why the Green's function has these two terms, which in short can be written in this way, where I have introduced a so-called time ordering operator. Okay, so this is the definition of the Green's function. Next, we made a connection between the Green's function and the quasi-particle energies that are measured in, for example, a photoemission experiment. And what we derived was the following expression for the Green's function in frequency space. And the important bit here, so this is an exact result, so no approximations whatsoever. And the important finding was that the poles of the Green's function in frequency space are precisely the quasi-particle energies that are measured in photoemission and tunneling and transport experiments. So this is why the Green's function is such an important quantity, because of this property. We also looked at the Green's function when we neglect electron-electron interactions. In that case, it's quite easy to calculate, and it can be expressed in terms of the Kohn-Sham energies and the Kohn-Sham orbitals in this way. And finally, we noted that when we express the non-interacting Green's function in a basis of Kohn-Sham orbitals, it is a diagonal matrix. So then at the end of last week's lecture, we asked ourselves, so how can we now calculate the interacting Green's function? So it's quite easy to calculate the non-interacting Green's function, as I just described, but how can we include the effect of interactions? And the sort of approach that we took was to use perturbation theory. So basically, everywhere where there is a Hamiltonian in the Green's function, we split the Hamiltonian into a part for non-interacting electrons and a part that includes electron-electron interactions, and expand that term in a Taylor series. Now, you could and maybe you should be very suspicious of this procedure, because the Coulomb interaction by no means is a weak interaction. So sort of truncating this series potentially is not clear how reliable the results are that you would obtain from this. But from a more practical point of view, when you do this expansion, you generate a lot of terms. So if we go back to the Green's, where is it? So here is the Green's function, and here you see all of these exponentials. When you expand all of these exponentials in terms of a Taylor series, you generate a lot of terms, and the bookkeeping can become quite tricky. And that is the reason why Richard Feynman came up with a graphical representation of these terms, which are known as Feynman diagrams. And at the very end of last week's lecture, we basically introduced how these Feynman diagrams are constructed. They have three ingredients. The first ingredient is the interacting Green's function G, which we describe by an arrow like by a straight line, by a double straight line like this. And that's the quantity that we want to calculate. We also have the non-interacting Green's function G0, which we can calculate, for example, easily from a DFT calculation, which we describe by a single solid line. And then, of course, the quantity that connects the interacting and the non-interacting Green's function is the interaction, which here is just the Coulomb interaction, which we'll describe by a wiggly line. And of course, the goal is to express the interacting Green's function in terms of the non-interacting one and the Coulomb interaction. And there's a sort of a well-defined procedure for doing that. The first step is to draw all topologically distinct connected diagrams with n interactions and 2n+1 G0 lines. And so this is what I did. So here you see the term where there are no interaction lines and one G0 line. So that's, of course, the easy bit. Next, at first order, we have one interaction line and three G0 lines, and there's two diagrams, this one and this one. And then at second order, but we have two interaction lines and five G0 lines. Actually, there's already like a whole zoo of different diagrams. So you can appreciate that the complexity increases very quickly as we go to higher and higher order in this perturbation theory. Okay, so this is basically how far we got in the last lecture. So are there any questions at this point? Doesn't look like it. Okay, so then we'll basically go to the next step of this procedure. So that is, once you have drawn all these diagrams up to a given order, we want to know how to evaluate these diagrams. And the first step is to label each point where interaction and G0 lines meet by a position and a time. Each point. So each point is a, you know, we label each point by a position and a time. So for example, so here is such a point where G0 lines and interaction lines meet, and here's another one. So we will call this point R1, T1, for example, and this one R2, T2. And similar in this diagram, we have, again, 2 points where these meet. So we'll call this one, again, R1, T1, and this one R2, T2. And here, of course, you can see there is more of these lines. There's more such points where they meet. Okay, so that was step 2. There's 2 more steps. So step 3 is we was going to write down a product of interactions and G0s. For this diagram, and then integrate over these intermediate space-time points. And then the last step is just we're going to multiply by a factor of -1 to the f, with f being the number of closed G0 loops. So for example, you see, so this diagram, for example, has a closed loop. This one has, for example, 2. So we have to include that factor. All right, so let me just be specific and show you how to apply this procedure for the first order terms. So, so at the first order, we have basically, I'm just going to redraw them. We have these diagrams, R1, T1, R2, T2, R prime, T prime, and we've got the interaction line. And basically, what we have to do is we have to we have basically a G0 line from this space-time point to this one. So that is R prime, T prime, R2, T2. Then we have an interaction line from this space-time point to this one, right? So this would be V R2, T2, R1, T1. Then we have a Green's function line, a G0 line, which again connects these 2 points. So this is again a G0, R2, T2, R1, T1. And then we have another Green's function line that connects basically R1, T1 with RT. So that would just be G0, R1, T1, RT. So that was so that's just writing down these G zeros and this one interaction. And then the second step also says that we have to integrate over the intermediate points. So we're going to have a dr1, dt1, dr2, dt2. And since there is no closed loop in this diagram, that is the end of it. So that is the analytical expression corresponding to one of these first order diagrams. Well, I guess you could ask, so what does this mean? What's the physics of this term? We can sort of get a glimpse for the physics.
So basically, very similar, but I want it short. Like I want it pretty, like not a bob, because I want it really layered, and I want like a fringe sort of, because I part in the middle, and then I want to, yeah, very like, yeah, sort of. And,
is there, sorry, can you mute yourselves?
Like
I can hear
a little bit more at the front, especially. And yeah.
Let me see. Okay. All right. Thanks. Everybody muted again. Okay. Good. Then we can continue. All right. So that was the one. That was the one of the first order terms, and we were just about to ask ourselves, what is the physical meaning of this term? What is the physical content? And to see this, we basically inspect sort of these contributions in the middle. So we have this product of V and G0. And so if we look at that product, well, and sort of in G0, we know we have sort of this sum over the Cohen-Sham states like this. This is V0, this is G0, and then we have a Coulomb interaction, something like this. And when we look at this term, you see that this one actually looks a lot like the exchange potential in Hartree-Fock. So this diagram actually describes exact exchange. Now, what about the other one? So the other one looked like this. So we go from R to T, and we've got R1 T1, and we've got R prime T prime, and we've got our interaction, and then we have our bubble R2 T2, right? So that was the other first order diagram. And again, we use this, we write down the G nodes and the interaction lines corresponding to these space-time points. So we've got a G node, R prime T prime, R1 T1. We've got a Coulomb interaction, R1 T1 to R2 T2, right? And then we've got another G naught. So this one is this G naught that makes up this closed loop, and that of course has an R2 T2 R2 T2 argument, right? Because it starts and ends at the same point. And then we've got one more G naught, which is R1 T1 RT, right? So I've written all the Green's functions and interactions down with the correct space-time points. And then I need to again do this integral dr1 dt1 dr2 dt2. And finally, I have to multiply with -1 because I have one closed loop in this diagram. All right, so you know that is the other first order diagram. Again, you might ask yourselves, what is the physical content of this diagram? And so again, we will look at this Coulomb interaction line and this G naught line in the middle. And so again, we will have a sum over states. We've got a psi n R2 and then another psi n R2, right? And then we've got something like this. We have our Coulomb interaction. And I will also bring down this integral over R2 here. Yeah. And if we look at the structure of this term, what we see is that we have a product of wave functions, which basically give us a density. And then we calculate the potential that this density creates. And this potential is what we typically call the Hartree potential, right? So this diagram is basically the diagram that gives rise to Hartree interactions. So we've got the top one is a diagram that describes Fock exchange, and this one is a diagram that describes Hartree interactions. And of course, you are free to sort of try to write down the analytical expressions for, let's say, the n equals 2 terms, but you can quickly see that this becomes a bit of a nightmare, and the expressions become very, very long and hard to manage. So what we'll actually prefer to do is work with the diagrams directly and basically manipulate them rather than work with the analytical expressions that they correspond to. And that is actually quite elegant and easy. So let's try to do that. So what we'll try to find is if there is in this infinite diagrammatic expansion of the interacting Green's function, if there is any hidden structure. And what we'll find is there is a lot of hidden structure that can be exploited. The first thing that we'll note is that when I look at these diagrams, all the diagrams have basically the same structure, or they have one commonality, and that is they have an incoming G0 line. Then something happens, and that can be quite complicated, and this involves interactions. But at the end of the day, each diagram has an outgoing Green's function line. And that is true for each and every diagram that I've drawn, except I guess for the trivial one, which is trivial because it has no interactions whatsoever. So what does that mean? It means that I can write the interacting Green's function, again, which I remind you is represented by this double line, as the non-interacting Green's function plus a term that I can write like this, an incoming Green's function line, then a bubble which contains, everything, all possible intermediate bits, and an outgoing Green's function line, and nothing else. So all the complexity now is inside this bubble, which contains basically the intermediate parts of all the diagrams, right? So it looks like this. So it's basically what you get when you take these diagrams and you cut off their incoming and outgoing Green's function lines. Right. So I can represent this infinite series in this very simple way by these, two terms. Okay. What more? Now, when I look at these terms inside this, and I'll actually draw it like this, just to distinguish it from something else. So when I look at these diagrams, I can see that they fall into two classes. One class of diagrams can be separated into two diagrams by cutting an interaction line, by cutting a Green's function line. So for example, if I take a scissor and cut this diagram in the middle here, it separates into two different diagrams. And similarly, if I take a scissor and cut this G0 line, again, the diagram fractures into two separate diagrams. However, when I look at the other diagrams, that's not possible, right? I can take a scissor and I can cut here, or I can take a scissor and cut here, or I can cut here, but none of these cuts will actually separate or separate this diagram into two fragments. So there are these very fundamental classes of diagrams. So some diagrams right. So that is, of course, a very fundamental observation that this is possible. Now, what does this mean then for the structure of this bubble here, which contains all the effects of electron-electron interactions? It means that this bubble can be expressed in the following way, basically as a bubble like this, where I just draw sort of one set of lines, which we'll actually see that corresponds to the self-energy in GW. This is the self-energy sigma, which has the property that it only connects diagrams which cannot be cut. Plus, basically, the self-energy, two self-energies connected by Green's function lines, and and then the same with 3, and so on and so forth. Right. So we can express this bubble that contains all diagrams in terms of this self-energy, which only connects the diagrams that cannot be cut, and a G0 line. Okay, so again, we're revealing a lot of structure. What happens now if we take this result and plug it back into the equation up here, right? So let's see what we get. So again, we should never forget that what we're trying to calculate is the interacting Green's function. And we said that we can write it in this way. There's a G0 line, and now I'm replacing this bubble that contains all diagrams by the self-energy, which only contains the diagrams that cannot be cut into two pieces, right? And then I get a series like this. What is interesting is that I can write this series in the following way. I can sort of disconnect sort of this part with the G0 line and the self-energy, and put everything else into this bracket. And when I look at what's inside this bracket, this is, of course, nothing but the interacting Green's function itself, right? So the equation that we have derived now is the following. right? And this is the famous Dyson equation for the interacting Green's function. And you know, it's really nice how we have derived this very, very deep equation, obviously, just by, you know, looking at and manipulating the structure of these diagrams. So it's a very elegant approach. Of course, at any time we can use our Feynman Feynman rules to translate any diagrammatic expression into an actual equation. So if we do this for this expression, and again we have to sort of follow the steps where we sort of attach points to it, where we attach space-time points to everything, like this, and then sort of we just follow the rules. We can derive the following equation for the interacting Green's function. Again, we have to integrate over all intermediate space-time points. Now we have the self-energy sigma. And then we have an interacting Green's function line G, like this, right? So this is the analytical expression, which is equivalent to this diagrammatic equation, and is known as the Dyson equation for the interacting Green's function. Okay, we can simplify this equation a little bit. How can we do that? So what we'll do is the following. We will do a Fourier transform. And we will express these Green's functions and self-energies in a basis of cone-sham orbitals. We have established in the last lecture that the non-interacting Green's function is a diagonal matrix in that basis. And it turns out that it is often a good assumption to treat also sigma and G as diagonal in the spaces of cone-sham orbitals. But it's not always true, but very often it is. And if that's the case, we can write the Dyson equation in the following form. So we've got the diagonal component of the Green's function, this function of frequency, is equal to the diagonal component of the non-interacting Green's function plus this product here. Right? So we've just Fourier transformed and expressed this in a basis. And now what we can do is we can solve that equation for the interacting Green's function. And what we'll get is the following, that the inverse of G and N is equal to the inverse of G naught and N plus the self-energy sigma NN omega. Okay, couple of things that we can note. So we know that the inverse of G naught, so coming back to our result here, so the inverse of G naught is just omega minus epsilon n. This is omega minus epsilon n. And the other thing is that what we want to calculate at the end of the day are these quasi-particle energies, right? And we have established in the last lecture that the quasi-particle energies are the poles of the interacting Green's function, or in other words, they are the zeros of the inverse of the interacting Green's function, right? So so that's true. And so we can derive the following equation for the quasi-particle energies, namely that EGW is equal to, all right, so we have 0 on the left-hand side. We set omega equal to the GW energies. Right, so we can derive, so this is the equation for the quasi-particle energies that are measured, for example, in a photoemission experiment. And we can arrange this equation to make it look more familiar. You can write it in this way. Right, and in this way, it looks very similar to the equation that we wrote down in the beginning of last lecture. So, so here we basically established that this is the equation that relates the Kohn-Sham energies to the GW energies. Now, there's one difference here, as you probably noted. There is this, we subtract this exchange correlation potential here, which is for some reason, where is it? Which is not, so this subtraction doesn't seem to be happening here. Now the reason is quite simple, and that is because these energies here are the energies of the truly non-interacting electrons, right? While in the Kohn-Sham energies, we already have included some interactions, namely Hartree interactions and DFT exchange correlation interactions. So to sort of to derive that expression from the last lecture, we have to do two things. So first of all, we have to separate the self energy into a Hartree part and the rest, which are called sigma GW. And as I've shown you, so the Hartree part is just this diagram here. So this diagram is the Hartree diagram, which I can separate out. So I can write my self energy as this Hartree part and the rest, which I call sigma GW, and then I can add and subtract the DFT exchange correlation potential. And basically the Kohn-Sham energies are given by the non-interacting energies plus right? And so I can write, I can then relate my GW energies to my Kohn-Sham energies in this way. Precisely as established in last week's lecture. Okay, any questions so far? Let's see, nothing in the chat. Okay. Okay, good. All right. So still though, we haven't made any assumptions, right? Everything that we have done so far is still exact, because we assume that all diagrams up to infinite order are contained in the self energy. So far, no approximations have been made. The only small approximations that we have made is the assumption that that the self energy is diagonal in the cone-sham orbitals. But again, that is an assumption that we do not need to make if we don't want to. Okay, but now is the time to think about how we can approximate the self energies. In other words, which diagrams in this complicated infinite series should we retain and go through the effort of actually evaluating, and which diagrams can we neglect? So the simplest thing is, to go order by order. So that is keep only up to n equals 1 terms, right? And then basically what we get is that the self energy is a sum of these two diagrams, each one having one interaction lines. But I already told you that this diagram is related to Fock exact exchange, and this diagram is related to Hartree interactions. So what we get, so this theory is nothing but Hartree-Fock. Okay, you might say, okay, we've gone through a lot of trouble of deriving Hartree-Fock, which is something that is really old, and more importantly, we already know that it's not a very useful theory because it lacks screening, right? That was the whole motivation for going beyond Hartree-Fock. Okay, so how do we bring back screening? And so screening basically means that we have to replace our bare Coulomb interaction with a screen interaction. So what we might be tempted to do is look for diagrams that have a similar structure as this one, but sort of contain, but are at higher order. So and there are actually diagrams that do fulfill this criterion. So this is the Hartree-Fock exchange. But then we could look for there's, for example, a diagram that looks like this, right? So it has sort of a similar structure, but it has this extra Green's function bubble in the middle here. And of course, there is a whole set of diagrams that are similar, but more complicated. So instead of just inserting a single Green's function bubble, I can insert two, or I can keep going with this. And basically, when we sum this infinite series of diagrams, what we can define is an effective diagram with a screen interaction. So this double wiggly line is what I'll use for the screen interaction. So this is the definition of the screen interaction, and this is this sum of sort of diagrams with more and more bubbles is known as the random phase approximation. And last week somebody asked, are all the diagrams equally important, or how do I know which ones are more important and less important? And basically one of the very important results in sort of the historical context of many-body theory was the proof that that this set of diagrams, the random phase approximation, is the most important one for the electron gas at high density. So you can convince yourself that these diagrams are the dominant ones when you're dealing with a high density system. So a system where you have a high concentration of electrons. Okay, so let's look at this a bit more. So we have defined this double wiggly line W. So this is again the screen interaction in the following way, sort of as the bare interaction plus the bare interaction with a bubble, and then, you know, two bubbles and so on and so forth. Again, we can see that this equation has a similar structure as the equation for the interacting Green's function. In particular, we can write it in the following way. We can separate out this left part of the diagram and put the rest into this bubble. Into this bracket. And what we'll note, of course, is that the stuff in the bracket is nothing but this green interaction again. So what we get is again an equation that is very similar to the Dyson equation for the Green's function. And it looks like this, right? So this is basically the Dyson equation for the screen interaction. Again, you know, what is nice is that we have arrived at this just by diagrammatic arguments, without ever, you know, having to write down an equation. So this is again a very nice way to do science, I think. But of course, at the end of the day, you know, we might want to go back to, you know, writing down an analytical equation. And we can again do this by doing a Fourier transform to frequency space and using a basis. So it could be a basis of cone-sham orbitals, or it could be some other basis. It turns out for the screen interaction, though, it's not a good approximation to assume that these that everything's diagonal. So we'll have to keep the full matrix structure, which I'll express, you know, I'll denote by these. So I'll denote matrices in the orbital index by this, by these double lines.
You have a question, Johannes?
Oh yeah, I see something in the chat. Do the bubbles share equal weight? Are you asking if all bubbles are the same?
Yeah, I am.
Yeah, so the bubble is, all bubbles are the same. So they are just, I guess you could say they have equal weight. They are the same thing. So I'll tell you in a second what the bubbles are. So what we have is the matrix representing the screen interaction, the matrix representing the bare Coulomb interaction, plus sort of this term that is the product of the bare Coulomb interaction, the bubble, which I'll express as chi0. So this is the symbol that I'll give to the bubble, and then another screen interaction, W. So, and again, I can rearrange this equation a little bit to solve for the screen interaction. And what I get is the following. So I can write this as the one matrix minus the chi0 omega inverse acting on V. So I've just, you know, solved this equation for the screen interaction matrix, and then I can define this stuff in the parentheses is typically called the so-called dielectric matrix epsilon that acts on the Coulomb interaction, right? So, I mean, you know, in simple electrostatics, you would just multiply the screen interaction by 1 over epsilon. If you have 2 charges in a homogeneous dielectric, it would be as simple as that. And microscopically, you know, screening isn't quite that simple. You have to, instead of sort of just a dielectric constant, you have a frequency-dependent dielectric matrix that you have to deal with. So it's significantly more complicated, but that's what it is. All right, and then finally, I told you that we basically represented this bubble in the diagrams by this symbol, by this mathematical symbol chi0, and chi, what is chi0, can be interpreted as the density response function of non-interacting electrons, right? I mean, obviously, chi0 consists of 2 G0 lines, and so the bubble doesn't include any interactions. So it must be some property of non-interacting electrons, and what it is actually their density response function. So let me just write this down. So chi0 R1 T1 R2 T2 is given by, so again using the Feynman rules, R1 T1 R2 T2 G0 R2 T2 R1 T1, and it is the density response function of non-interacting electrons. And again, this is if we go back to how we introduced screening in last week's lecture. What we did was something not too dissimilar. What we said is basically here we said that the screen interaction is the bare interaction plus basically the contribution from this polarization charge density delta rho, and the polarization charge density is described by this density response function chi. So this intuition is precisely reflected in our finding here in sort of how we can express the screen interaction here. Okay, so so where does that leave us? So what we have is we've got sigma, and basically what we have done, we have written sigma as the Hartree term, so we separated that out, plus this exchange diagram, where now though we have replaced the bare Coulomb interaction in the exchange by a screen Coulomb interaction. And that is what's known as, so more precisely, this diagram here is what's known as the G0 W self-energy. Okay. And again, I can express this in, I can use my Feynman rules to represent this, you know, these diagrams by equations. So the first term is just the Hartree potential, and the second term though is something I can write as I G0 R prime T RT R prime T prime W RT R prime T prime. So again, this is This is just using the Feynman rules to represent this diagrammatic formula by an analytic expression. Okay, and any questions so far? No? Okay. There's just one more thing I want to say, and then we'll take a couple of minutes break. You can, so what we have done essentially is we have summed an infinite series of diagrams, basically this random phase approximation. And so we've basically subsumed an infinite set of diagrams into a single effective one. You can go even further and sum another and include even more diagrams into this effective diagram. And that can be done by replacing the G0 line here by an interacting Green's function line. And this is known as the full GW. So again, it's full GW diagram by replacing so the full GW diagram would be this diagram. Right. And basically you can expand both the screen interaction and the interacting Green's function in terms of elementary diagrams, and in that way you can generate a very large a number of these elementary diagrams simply by evaluating this effective diagram. Okay. Any questions so far? I guess that there were none. So what we'll do now is, I guess we'll take a couple of minutes break. People can grab a coffee or have a stretch, and maybe we'll continue in 5 minutes. So 2:10. So we'll continue. All right, thanks guys, see you in a couple of minutes. Right. Okay. Let's continue to the last bit. I guess I should share my screen again. There was something in the chat. Okay, that isn't relevant to me. Share screen. There we go. Good. All right. So let's briefly recap what we have achieved now. So we set out with the following problem. We wanted to calculate the interacting Green's function G because its poles and frequency space give rise to the, give us the quasi-particle energies, which are relevant for many experiments, and we ended up with this very unwieldy and complicated set of diagrams. We learned how to, map these diagrams onto analytical expressions using the Feynman rules, and then we set out to find structure in this diagrammatic series. And the first important result was the Dyson equation, which basically allowed us to express the interacting Green's function in terms of the non-interacting one, and the self-energy, which only contains diagrams that cannot be cut into two bits, that cannot be separated into two fragments by cutting a single Green's function line. And when we analyzed this equation a bit further, we recovered basically, and the equation for the quasi-particle energies that relates the quasi-particle energies to the Cohen-Sham energies that we discussed last time. And so basically what's nice about this equation, it starts with the Cohen-Sham energies, which we know aren't really physical things. And you can correct these Cohen-Sham energies to get true quasi-particle energies. So that is a very useful equation, and basically maybe a little bit magical to turn something non-physical into something physical. But then the final challenge is to actually say what diagrams do we keep in our self-energy. We understood that keeping the lowest order leads to Hartree-Fock, which lacks screening. So we had to include screening, which we did using this random phase approximation, and finding the Dyson equation for the screen interaction, which gives us this G0 W self-energy. And finally, the full GW self-energy is obtained by replacing G0 in this diagram by the fully interacting Green's function. Okay, so that's what we did. Okay, so let's analyze this a bit more. Basically, what we need, of course, is at the end of the day, we need the self-energy and frequency space, right? But here we have it in, in time space. So we need to Fourier transform. And when we look at this expression here, you see that you have a product. We multiply G0 at time t and t prime with W at t and t prime. So you've got a product in time space. So what that means when you Fourier transform is you get a convolution in a frequency space. So when I do sigma GW, I get the following. So I get a convolution in frequency space. Right, like this. Okay, now I have to deal with this integral over frequencies. But I also know that G0 has poles, right? So when I look at G naught as a function of a frequency, well, I'm just going to write it down again. It looks like this: psi nr prime star. And then I have something like omega minus omega prime minus epsilon n plus minus I eta. So that is this expression. And you see G naught has poles, right? When I look at it as function of frequency, there are certain frequencies where poles occur. And so when I use my complex analysis to do this integral, basically using the method of residues, these poles will give me the contribution to this integral. So what I get then is GWRR prime omega. So I have poles in G naught, and they give me the following contribution. I have a sum over occupied states, psi nr prime star W R prime omega minus epsilon n, which is what we have, what I introduced last time as the screened exchange term. The screened exchange term is basically what you get when you pick up the poles from the Green's function. But we also know that the screened exchange isn't the full story. There is another term called the Coulomb hole term. Where does this come from? Well, there's only one possibility, and that is that the screen interaction also has some poles. And without going into sort of the full mathematical detail of it, I will just tell you that when you evaluate the contribution of the poles from the screen interaction, you get another contribution, which looks like this. Pi, then you've got the imaginary part of the screen interaction at omega bar, omega minus omega bar minus epsilon n plus I eta. Right, so this second term, which is the so-called Coulomb hole term, arises from the poles of the screen interaction. There's an important difference here, and that is the screen exchange term. You only have a sum over the occupied bands, exactly as you would have in Hartree-Fock, while in the Coulomb hole term, there is no such restriction. And so, yes, you sum over both occupied and unoccupied terms. In addition, you have to deal with this frequency integration. Okay. So that is sort of so typically, though, at least in the past, people often use additional approximation to make this expression a little bit easier to evaluate. Nowadays, actually, very often, no additional approximations are used to evaluate this self energy. But let's just see what these additional approximations are. So the one is the use of a so-called plasmon pole approximation. And that is basically an approximation that's usually quite good. So what is being assumed is that the imaginary part of the self energy as a function of frequency, which is basically the quantity that comes into the Coulomb hole term of the self-energy, is approximated by something proportional to a delta function. So basically, when I look at the self-energy, when I look at the screen interaction as function of frequency, it has one peak, and the frequency where this peak occurs is the plasmon frequency. And in many materials, this actually is a pretty good approximation. And of course, when you use that approximation, what happens is that you can carry out this integral over frequencies analytically, which makes your life significantly easier if you work numerically. So that is the plasmon pole approximation. And the second approximation that you see less often is called the so-called static Cossacks approximation. And you see it less often because it's less accurate, so it's usually not such a good approximation. And what is being assumed here is that the difference of the frequency at which we evaluate the self-energy and the Cohen-Sham energy is zero, right? So where does this become relevant? It becomes relevant when we look at the denominator of the Coulomb hole term, right? So we do have precisely this difference here. And the assumption is that that difference vanishes. Of course, that can't be true, right? If we're summing here over all possible states, then it cannot be true that for all states, that all states have an energy that's close to any frequency that we might be interested in. So it seems quite obvious that this is a more drastic approximation. What happens though, I mean, when we use that approximation, let's see what happens. So we get, so if we look at this term here, and basically, sets omega minus epsilon n to 0, what happens is that the integral becomes independent of n, of the orbital index n. And that means we can move that integral in front of the summation over n. So we get the following. Right? Now, though, nice things happen. The one nice thing is that this sum here by the completeless relation is just a delta function, delta r minus r prime. So we can do this infinite sum over Cohen-Sham states. We can carry it out analytically. And we can also carry out the frequency integral analytically because we can use the so-called Kramers-Kronig relation. By the so-called Kramers-Kronig relation, one can show that the integral just becomes a half the real part of the interaction evaluated at 0 frequency minus the bare interaction, and then we still have our delta function. So so that's that is the simplification that we can get when we invoke the static Cossacks approximation. And just for completeness, I mean, this is the analytic expression that I've shown you in the last lecture, right? So in the last lecture, I've shown you precisely this simplified version of the Coulomb Hall term that you obtain when you invoke the static Cossacks approximation. Okay, but as I said, and sort of, you know, modern GW, very often you don't have to invoke any of these approximations, and you can just, you know, numerically carry out this frequency integral. All right, are there any questions at this point? No? Okay, so I mean, this was basically what I wanted to do. So what I've achieved, what I've set out to do. I have shown you from the ground up how to derive this GW self energy, you know, by starting from Adam and Eve, meaning from truly non-interacting electrons, and including you know, and then developing techniques to deal with the bare Coulomb interaction. So, you know, I've fulfilled my promise. The last part of this lecture, I want to talk a little bit about GW in practice, just to give you a sense for, you know, I've sort of shown you the analytical derivation, but many of you might be interested at some point in doing an actual GW calculation of a material, maybe to calculate a band gap or something like that, or a band structure. And so it's good to talk about how in practice you would do such a calculation. So right now there's different codes that you can use. The one that I use is Berkeley GW, sort of a standard plane wave code, and there's a similar code called Yambo, and there's implementation in VASP. So there's some quantum chemistry implementation, MOL GW. There's an new implementation in TurboMol. There are things like Questal. So actually, there's now quite a number of codes that you can pick from. There are some slight differences, in particular when it comes to the basis that is being used, and also to the treatment of, you know, these additional approximations and whatnot. You'd have to choose carefully. But you know, in all of these codes, most of these codes go through a similar set of steps, and invariably the first step is you start with a DFT calculation. Potentially could also be some other type of mean field calculations. Could also be a Hartree-Fock calculation, or a DFT plus U, or a, you know, hybrid calculation. Any of those. The important thing, though, that might be a little bit unconventional, is that you would need both the occupied states and the empty cone-sham states. So typically, we don't care so much about the empty cone-sham states. Maybe we care sort of, you know, about some unoccupied states, you know, close to the band gap. But here in these GW calculations, we often need hundreds or even thousands of these unoccupied cone-sham orbitals, simply because, you know, because in the Coulomb Hall term, there is no restriction to unoccupied orbitals. So, and that and sometimes that's already the problem, that you can be quite difficult to converge these DFT calculations if you want to calculate, let's say, 5,000 unoccupied states. At least from my experience, sometimes that is actually already a big problem. So that's the first step that basically has nothing to do really with GW. Then the second step is to construct the screen interaction. So what do you need to do for that? Well, let's have a look. So the screen interaction is obtained by solving this Dyson equation here. And the Dyson equation involves 2 bits, right? The Baire-Coulomb interaction, okay, that's easy. It's just 1 over R. But it also involves this density response function of non-interacting electrons, which is calculated in this way as basically the product of 2 non-interacting Green's functions. And again, each non-interacting Green's function contains a sum over both. Where is it? So each non-interacting Green's function contains a sum over all Cohen-Sham states, both occupied and unoccupied. So what you need to do here is evaluate chi0. And again, you could run into the problem that the problem is that you encounter slow convergence with respect to the number of empty states. But that's the first step. Once we have chi0, well, we can obviously calculate the dielectric matrix. Right? And well, once we have the dielectric matrix, we can calculate the screen interaction epsilon inverse V. Now, there's another problem, and that is which, we have to use a basis here, right? These are matrices in some basis, and we'll have to choose what kind of basis to use, right? I mean, we could use a basis of Cohen-Sham orbitals. That is typically the procedure that's being used in quantum chemistry codes. In sort of solid state GW codes, you will more frequently encounter a basis of plane waves. And then the question is, how many plane wave, how big a plane wave basis do you need? And again, that would be a convergence parameter. So now it turns out, though, that these 2 problems here are actually not unconnected. So it turns out, in fact, that they are strongly coupled because, if you have high energy states, those states typically are very oscillatory. And if states are very oscillatory, you need, for example, a lot of plane waves to represent them. So this issue of the slow convergence with respect to the number of empty states and the convergence with respect to the basis size, these 2 problems are in fact strongly coupled problems. And that's sort of something that can cause a lot of difficulties because they can lead to unphysical convergence. So for example, what very often has been done in the past is that people use a relatively small bases to represent the screen interaction, and then they find that they need to sum over relatively few empty states to get convergence. But the issue is, had they used a bigger basis size, then they would have needed more empty states to converge it. And so they basically think they are converged, but in fact they aren't. And then they get incorrect numbers out of their calculation. So, something to be quite careful, you need to be quite careful here. Okay, so now we have the screen interactions hopefully converged. Again, you would have to make a choice though. Typically, is this a choice between a plasma and pole model or a so-called full frequency calculation? So full frequency means, no plasma and pole model, and you would have to do this. You would have to do this frequency integral in the Coulomb whole term numerically. If you decide to go with the full frequency version, you will have to calculate the screen interaction on a frequency grid, and of course that frequency grid has to be sufficiently fine and sufficiently large to carry out this integral accurately. So that is another thing that you need to worry about if you decide to go down the route of a full frequency calculation. Okay, but and then there's just one more step. Step 3 is basically you construct the self energy. And evaluate the quasi-particle equation, right? So you evaluate this equation here. And that is the final step. So so that is how. So those are the typical steps in a GW calculation. In sort of these standard codes that I've mentioned up here. All right, I think that was all I wanted to say for these 2 lectures. Are there any questions? All right. If there are no questions, you can always shoot me an email. I think the lecture has been recorded and will be uploaded, and you will probably receive a link from Karen. And well, I hope you'll do a GW calculation at some point in your future, and hopefully you'll understand what you're doing. So thanks very much for attending and paying attention, and take care, everyone. Bye-bye.